first to thank the organizer for inviting me to give this talk. And during this talk, we'll speak about the nucleosynthesis of light and heavy elements across the galaxy. In particular, we'll focus on neutron star mergers and asymptotic giant branch stars. So I will provide you with a brief explanation, summary of what the nucleosynthesis of heavy elements, heavier than iron, is, and in particular concentrating on neutron capture processes. That is the slow neutron capture process, the S process, and the rapid neutron capture process, which is the R process. The first process is active mainly in asymptotic giant branch stars, which are the final evolutionary phase of low mass stars, low intermediate mass stars, and I will focus on the parent stars of presolar silicon carbide grains and on the effects of mixing triggered by magnetic fields in these stars. And then I will deal with the neutron star mergers and the production of light elements in these objects. So first of all, let me introduce you to neutron capture reactions. It is basically impossible to synthesize elements heavier than iron via charged particle reaction because of the Coulombian barrier. This problem can be overcome if neutrons are the particle considered. In this case, there's no Coulomb barrier to be overcome, and heavy elements capture neutrons very easily, and this can occur even at extremely low energies. In this case, the problem is mainly related to the availability of neutrons, in the sense that we have to find an environment which is providing a large neutron flux for enough time to lead to the synthesis of heavy elements. In principle, you may expect to find a very large range of stellar neutron fluxes in stellar objects. Actually, and it's the contrary, in the sense that the most common fluxes are either quite small or quite large, and they refer basically to the slow neutron capture process, the S process, and to the rapid neutron capture process, the R process. If we concentrate on the plot in the middle of the figure, you can easily recognize which is the difference between these two processes. So let's start from a stable nucleus, which is capturing a neutron, and lead to this neutron capture leads to the synthesis of an unstable isotope. Depending whether the beta decay time scale is lower or larger with respect to the neutron time scale, neutron capture time scale, you can have different paths. In the case of the S process, the nucleus will decay to its stable isobar. In the case of the R process, you will proceed synthesizing isotopes enriched in neutrons. And if we have a look to the nuclide charts, we see that the S process is basically moving along the so-called beta stability valley, so it lays close to the stable isotopes, while the R process can produce very enriched, very neutron-rich isotopes up to the drip line. And this is how the two processes are working. The S process mainly occurs in asymptotic giant branch stars. So this evolutionary phase characterizes the final phase of low and intermediate mass stars. That is, stars with a mass about lower than about 8-9 solar masses. And as you can see, those stars are very cool and expanded. The fact that in these stars are very cool allow to the fact that in their external layers molecules can form, and also not only simple molecules but also cluster of molecules up to the formation of dust. In fact, AGB stars are among the major dust producers in the universe. The dust expelled by this system can contain the isotopic imprint of the nucleosynthesis occurred in their interior. Some of this dust traveled in the interstellar medium and was captured by the protosolar nebula. And some of these dust particles were captured in meteorites. These meteorites then, giga-years later, fell to the Earth, and thanks to very nice experimental techniques, they can be isolated from the solar material surrounding them, and we can gain hints on the nucleosynthesis occurred in these parent stars. The study of these grains is extremely important because those grains are able to put very strict constraints to stellar models, in particular due to the fact that the uncertainties in the measurements are very low, about 10%, which is definitely, they are definitely lower with respect to spectroscopic error bars, which in some cases are even a factor of 2. They provide infos on isotopic abundances, but there are weakness points. In particular, we cannot have infos on the absolute abundance of the elements, and most importantly, we have to guess which was the parent star that polluted, that formed the grain, because we cannot define nor the mass nor the metallicity of these stars. For this reason, we started a project aimed at determining which are the progenitor of presolar silicon carbide grains. Silicon carbide is the most important species created in asymptotic giant branch stars. So if we have a look to the age metallicity relation in the solar neighborhood, we may be tempted to conclude that this relation is flat, and that in the last giga years, such a relation barely evolved over time. However, the temporal evolution of the metallicity of the local stars in the solar neighborhood is also driven by dynamical processes such as stellar migration, which is able to shape the distribution of stars in the solar vicinity over time. In fact, the local AMR is largely controlled by long-lived stars, a large fraction of which migrated from the inner disks, that is, from an environment where the metallicity is higher. For this reason, we decided to quantify the number of AGB stars close to the Sun's birthplace at the epoch of its formation via a chemodynamical model in which stellar migration is taken into account. Then we adopted stellar evolutionary models taken from the Fruity database, and we calculate the dust silicon carbide yields by using a dust growth code. So for the first time, we coupled these three components. What we found is that the silicon carbide production at the epoch of the solar system formation is dominated by contributions from AGB stars with about a initial mass of 2 solar masses and a metallicity close to solar. In particular, we also obtained a very nice agreement by studying the dimension of these grains. And here is the model in orange, the model distribution, and the blue histogram represents the grain data. As you can see, the agreement is quite good. Once we determined the masses and the metallicity of these parent stars, we checked if the models are able to reproduce the isotopic ratios measured in these stars. This is the typical notation for this measurement, which basically provides you the deviation from the solar ratio, which is 0 in both axes. As you can see, fruity models are the blue points. For some of them, the situation is good, but for some others, not. Then we implemented the the physics inputs of our models, and we could arrive to a situation where most of the some grains were good, but some others not yet. For this reason, we decided to investigate on other mixing episodes able to shape the so-called carbon-13 pocket, which is the main neutron source in AGB stars. In particular, we need some mechanism able to diffuse a small amount of protons from the cool and expanded convective hydrogen-rich envelope in the layer below, which are rich in carbon-12. The physical mechanisms proposed in the past were basically top-down mechanisms. That is, protons from the envelope penetrate down into the radiative layers. We instead decided to apply another mechanism, a bottom-up mechanism, in which magnetic fields are able to trigger the formation of magnetic flux tubes, which basically from bottom grows and capture some hydrogen in the convective envelope, and which are diffuses down for mass conservation. In 2014, Nucci e Busso proposed an exact solution to MHD equations under a couple of hypotheses. The first one was a simple geometry, that is a toroidal geometry, and the second was that the layers in which this equation were calculated, the density of this region has to behave as a power law of the radius. And this is actually the situation of AGB stars. What we found is represented here with the red points. You can see that in this case, with the proper calibration of the parameters related to the magnetic field, we find a good fit to all the ratios measured, which was not possible with the previous technique. And if we calculate a range of stellar models based on the assumption found by the results described above, you see that we are able to reproduce basically the whole distribution of grains. So magnetic fields are a very promising mechanism to explain the nucleosynthesis of AGB stars. Up to now, I just spoke about the S process, but actually also the half of the elements heavier than iron is synthesized via the R process. In the past, the R process contribution to the solar distribution was empirically determined as by subtracting the corresponding S process contribution. Why this? Well, simply because, as you can see in this plot, where it is reported as a function of the mass number, the product of the neutron capture cross-section times the solar abundance, you see that for the S process, you can find a sort of analytic solution. While for the R process, this is not possible. Well, this is basically due to the fact that the conditions in which the R process is working are definitely more complex and depends on many parameters. Here I reported the residual distribution obtained with the S processes yield calculated, described it before, and I compared them with some canonical R process calculation in which I varied the so-called YE, which is the electron to baryon ratio, which provides you how basically the degree of neutron richness of your plasma. And the idea is to try to fit the R process, the residual distribution, by computing R process nucleosynthesis calculation. With respect to the S process, there is another problem. That is, the search for the astrophysical environment is more delicate, as the physical conditions required are extreme. Up to now, the only stellar environment which has been demonstrated to host an in situ an ongoing R process are neutron star mergers. In fact, the electromagnetic counterpart of the gravitational wave detection GW170817 has been demonstrated to be in agreement with the heating rate and the opacity expected from a distribution of freshly synthesized R process element. A few days after the merger, the spectrum was compatible with the forest of lines expected for lanthanides and actinides. But at earlier epochs, at 1.5 days, it was suggested that strontium was present in the spectrum of this event. So a natural question arises: what about lighter elements? For this reason, we calculated the distribution of all the elements, focusing in particular on the abundances of the lighter ones, for three different systems in which we varied both the equation of state and the masses of the interactive neutron stars. Then we calculated the yields with the Skynet nucleosynthesis code, which is a free code, and here are the basically the results. What we found is that hydrogen and helium are the most abundant species, and they are comparable to strontium, to the lanthanides, and to the actinides, while elements between lithium and potassium are usually several orders of magnitudes less abundant. Interestingly, the case with unequal masses resemble basically what you could expect for a binary, for a neutron star black hole merger. And in this sense, this nucleosynthesis calculation could be used to characterize these events as soon as one of them will be detected and observed, basically, most importantly. What I reported here are the distribution of hydrogen, helium, lanthanides, and actinides in the YE entropy space parameter for a range of time scales for 1 milliseconds and after 11 milliseconds, which basically bracket the relevant time scale for the dynamical and spiral wave wind ejecta, which are the fastest ejecta expelled from the neutron star merger system. And what we find is that there is a region at low YE and for a low enough entropies in which lanthanides and actinides, which have been observed, are compatible to the presence of helium. Therefore, there is a situation in which all of these three components are present. The next question which arises is this an observable feature? We know that hydrogen and helium are synthesized as bare nuclei, but electrons recombine quite quickly. You think that about half a day after the merger, the temperature already decreased to 10 to the 4 Kelvin. So, as I already said, the spectrum of the electromagnetic counterpart of GW170817 at 1.5 days show a broad absorption feature at 810 nanometers, and this was explained by transition of strontium. This could also be consistent with a helium line.
Professor, you have
yes?
2 minutes left.
Yes, sure. It's the last slide. Thanks. With a helium line at 10,800 nanometers in the EACT expanding at 0.25 times the light velocity. We use TARDIS, the TARDIS code to test this, and we found that this feature is compatible with this absorption feature, but only in the case of very high masses expelled or under the condition on extreme non-LT condition. And thus we conclude that likely helium is not responsible for this observed feature, unless non-LT effects or the helium mass are severely underestimated. And similar results are obtained for hydrogen-rich EACT. So basically I come to the conclusion. I showed you that we determined the mass and metallicity distribution of pre-solar silicon carbide parent stars, and that this distribution is dominated by stars with an initial mass of about 2 solar masses and solar metallicity. I demonstrated that magnetic fields are able to shape the mixing in AGB stars in a proper way to reproduce the isotopic distribution of these grains. And finally, I showed you that we also studied the production of light elements in the EACT of binary neutron star merger, and we found a large production of hydrogen and helium, but despite that, their abundance is not so high, not high enough to explain the observed features. And so many thanks for your attention.